The other common situation for an improper integral is to look at the integral from 0 to infinity of 2 to the negative x dx or something similar. So basically when you're dealing with something that contains an infinity sign. And this means, how should you interpret this? What this actually means is the limit as t approaches infinity of the definite integral from 0 to t of whatever your function is. In this case, it'd be 2 to the negative x, but it could be any function. Now we're looking at the limit as t approaches infinity from 0 to t, 2 to the negative x dx. And again, even though this is a limit approaching infinity, this could be finite, it could be infinite. So here I've graphed 2 to the negative x, and I see, wow, that if I look at this area, that curve is decaying so quickly that it might be possible that I could take 1 or 2 or 3 or 5 gallons of paint and paint as much of this as I wanted to and never run out of. And let's go ahead and we can add Desmos. I'm curious if it can work with infinity. Okay, so it can by typing, you can type infdy, and it tells me that this definite integral, it approximates it as this number 2 to the negative x. It approximates it as this value 1.442695. Now we could use another tool. We could use Wolfram Alpha, see if it can do this improper integral as well. So wolframalpha.com is going to be looking at giving the definite integral from 0 to infty. Nope. Can I do infinity? There we go. I can click on this for infinity. By clicking the symbol next to the star, I can look at 2 to the negative x, 2 to the negative x dx, and I can ask you, all right, solve this. And it's going to tell me that the answer is 1 over natural log of 2. It gives the same decimal approximation, but Wolfram Alpha is actually able to give the exact value as well. And you have to remember here that when Wolfram Alpha talks about log, it always means natural log. So that's the common thing in math, that I don't know why I'm making these letters so much bigger, but it's the common thing here is that log of 2 actually means natural log of 2. Now I'm going to work through that and see how you can get that answer exactly on your own. So let's see what this answer actually looks like. And before we get too far, let's remember that we can rewrite this using properties of exponents as 2 to the negative 1 raised to the x. So we're going to do that, and it might make our lives even easier if we rewrite this as 1/2 raised to the x, because all of these things are equivalent. This part that I just did is just algebraic properties of exponents. So now the next thing you want to do is to look at this expression is equal to the limit as t approaches infinity of definite integral from 0 to t 1/2 raised to the x dx. I need to find this expression, and to do that I can use the fundamental theorem of calculus because now t is a finite number. So my antiderivative would be 1 over natural log of 1/2 times 1/2 to the x, and so I plug that into the bounds here, and I'm still keeping the limit as t approaches infinity, but now I'm going to plug this into the bounds, which gives me 1 over natural log of 1 over 2 times 1/2 raised to the t minus 1 over natural log of 1/2 times 1/2 raised to the 0. Now the only part of anything that depends on t is right here. So I have to look at what happens to 1/2 to the t as t gets bigger and bigger and bigger. Well, we actually already saw that with the curve that we graphed originally in Desmos, which was that this limit as 2 to the negative x approaches infinity, this limit is 0, just this part. So now I'm going to take the limit, and I'm going to get here that the answer is negative 1 over natural log 2 times 1/2 raised to the 0. I'm sorry, natural log of 1/2, because I rewrote this in terms of 1/2. So this is negative 1 over natural log of 1/2 times 1/2 to the 0. 1/2 to the 0 is equal to 1, so this just becomes negative 1 over natural log of 1/2. And then I'm going to finish up here. This is negative 1 over natural log 2 to the negative 1. And there's a property of exponents that says this negative 1 can come out. This becomes negative 1 over negative natural log of 2, which gives us our final answer of 1 over natural log of 2. So this down here, again, to do the cleanup portion, was also algebra, and that's okay. Algebra is important. But the ultimate thing that we have figured out is that this indefinite integral involving infinity actually takes on a finite value. And so the answer here is 1 over natural log of 2. Okay, now let's look at another example, which was the definite integral from 1 to x of 1 over square root of x dx. And what we can do here is look at this, say, okay, this is, I'm sorry, from 1 to infinity. So what we can do here is the definite integral from 1 to infinity of 1 over square root of x dx. And let's go ahead and rewrite this algebraically as x to the negative 1/2 dx. And then we're going to do the trick that we do where we're taking the limit as t approaches infinity. Our trouble spot here is at infinity, so let's replace it. Let's have the definite integral from 1 to t of x to the negative 1/2 dx. And let's just work on this for a minute. Our antiderivative here is going to be 1 over negative 1/2 plus 1 times x to the negative 1/2 plus 1. And when you clean this up, I'm going to go ahead and tell you that the antiderivative becomes big F of x is equal to 2 times x to the 1/2, or big F of x is equal to 2 times the square root of x. So then when I look at this, I can rewrite this expression. Now I'm still taking the limit as t approaches infinity. I can rewrite this expression as the limit as t approaches infinity, and I'm going to plug in my bounds of 2 square root of t minus 2 square root of 1. So what happens with this expression, 2 square root of t, as t goes to infinity? It keeps getting bigger and bigger and bigger. So this expression becomes positive infinity. This expression just stays as 2. And so the final answer would either be written as positive infinity, or we would say it diverges. And what that means is if we look at the area under the curve 1 over square root of x, this is you can see in comparing this to the curve that we just looked at, 2 to the negative x, how 1 over square root of x, you can see has a lot more area, and that area is not decreasing as rapidly. So it makes sense on some level, kind of intuitively, why this curve might have infinite area from 1 to infinity.